So thank you, everyone. Jake, we'll let you go and share your screen. I'll give a quick intro here. Thank you, everyone. My name is Chris Woldridge with Dorse & Company, one of the sales engineers, but apparently we're still not tech savvy enough at doing Teams calls after becoming professionals at this for 4 years. Today we are joined by our engineering support team at Dorse, John Neeson, Scott Boucher, and Blake Bonham. So thank you everyone for joining our Power Hour series. Today we have Jake Bamke, product manager for the DOAS group. So I know DOAS has some different meanings here in the Pacific Northwest. Some consider that preconditioners only of just energy recovery. Some consider that high percentage outdoor air units with heating and cooling. So hopefully you were able to join us for our energy recovery and pre-tempering presentation a few weeks back. Today, Jake is going to highlight our RV, RVE, RVC series of high percentage outdoor air units with and without energy recovery. So I've been lucky enough to work with Jake for many, many years, and I'm sure he's tired of hearing my voice. So with that, Jake, I'll let you go ahead and take it away.
Awesome, thank you. Never tired of hearing your voice, Chris. as long as there's compliments coming out of it too.
There you go.
Cool. Well, I appreciate everybody joining us today. I appreciate Dorse for holding these. So again, my name is Jake Bamke. I'm the product manager for our dedicated outdoor air systems business unit. Quite a bit to cover today. I'll see if I can get these to advance. There we go. So we'll start with just a real quick overview of what do we mean when we talk about outdoor air systems. We'll get into some cooling efficiency ratings and code updates that are coming and actually have been here for a little while as well. Talk more specifically on the air source heat pump, especially for the state of Washington. Get into pretty in depth into the low global warming potential refrigerant transition, and then finish up with some GreenHeck DOAS equipment stuff specifically. So feel free to send any questions along the way. Not sure how that works in this one. I'm guessing throughout the chat function, so I'll try to look a little bit. Otherwise, I'm sure the Dorse guys will do a good job of moderating that for me as well. So outdoor air equipment, what do we mean when we talk about outdoor air equipment, specifically on the DOAS side? So we're talking about packaged ventilation equipment that conditions, and then the big keywords are dehumidifies high percentages of outdoor air. And we actually break those up into two different things. One is that dehumidification process. So we do design our equipment to dehumidify down to about 50 to 55 degrees. Can go below that, don't have to dehumidify, but that's how our equipment is sized. And then when we talk about high percentages of outdoor air, we're really talking about anything about 25% outdoor air and above. Not saying that these units can't operate down to that 0% outdoor air, but from a size performance standpoint and the construction and the components that are used, really geared towards designing around that 25% to 100% outside air. Look at the common applications that we typically serve. I would say about half of our equipment go to education facilities. So seeing, air ventilation for classrooms, gyms, auditoriums, libraries. And then you get into some other corridor ventilation facilities like hotels, some multifamily residences, healthcare, food service, really any application where you're thinking about comfort cooling combined with high percentages of outdoor air required. So 3 main applications that we typically serve. The VAV type applications, first you start off with a single zone VAV, really have a single unit controlling temp and humidity for that space, but also providing that ventilation. And when we look at the supply fan in this case, typically we're modulating off of space temp. So we have a varying different levels or loads of space temp requirements. As more people come into the gym, more people leave the gym, it changes. We want to make sure that we can move enough air to control that temperature precisely. And then on the flip side, you have the ventilation to worry about as well. And in most cases, this is where we start to see some demand control ventilation, where your outdoor damper and recirculation damper are going to adjust based on the space CO2. So whatever space CO2 we're trying to maintain, dampers would automatically open or close based off of how much CO2 is built up in that space. When you get to the multi-zone VAV situation, now you still have a single unit. It's still controlling both the temp and the humidity, But then you have VAV boxes downstream that are allowing air to, more or less air, to get into those classrooms. So typically a temperature sensor tied to those VAV boxes going to open and close based on those classroom requirements and the amount of air that we need to cool down that space. But as those VAV boxes close, that means that those space set points are met, which means that we can reduce the supply fan speed. So you get really good part load fan savings from a multi-zone VAV application. Problem is, on low sensible days where you don't need as much air from a sensible standpoint, a little bit harder to control the humidity that might be building up in the classroom with the DOAS equipment. And then because you're modulating your supply fan, but in these situations, you still need a minimum amount of outside air percentage. Typically, we're seeing the outdoor damper track that supply fan speed. So as that supply fan ramps up and down, the outdoor damper will readjust positions as well to make sure we hit those minimum ventilation rates. So that multi-zone, if we look at, we're still serving multiple spaces, but then we really transition into what we see and what ASHRAE really calls a dedicated outdoor air system. So I know it's a little bit different in the state of Washington with DOAS, sometimes meaning only energy recovery, but still 100% outside air. In the cases that we look at these applications, we're really trying to decouple any systems that we have. So we have that outdoor unit, whether it's this DOAS unit here with cooling or heating, or if it's an energy recovery unit only, that is meant to provide all the ventilation. So it's providing it 100% outside air, distributing it to each individual space, and then something downstream will handle that temperature, that sensible load. This gives you really precise outdoor air delivery, so you're not overventilating the space, but it also gives you really precise temperature control as well. So temperature, latent or humidity, and your outdoor air percentage are all really controlled precisely with a true dedicated outdoor air system application. And where we're going with this is, obviously in a school, for example, I talked about education facilities, you might see one of these systems, or each of these systems in one school. And the biggest piece that changes is your cooling efficiencies that you have to look at. And the first one that we're likely a little bit more familiar with is our IEER. And this stands for Integrated Energy Efficiency Ratio, basically looking at 4 different conditions. So here we have point A, B, C, and D. They're weighted differently. So with these 4 outdoor conditions, I have an EER value that I can calculate from each one of these conditions. So for example, I would take the EER value at point A, I would take that times 0.02 and then combine that with the point from point B times 0.62 and get one integrated value. What you look at with this IER test is in each one of these points, the return air never changes. So what's entering our indoor coil is always going to be 80-degree dry bulb, 67-degree wet bulb. So it represents a true recirc type application, or if we think about those VAV type applications. The other thing to point out is IER is weighted to 98% part load conditions. So as our efficiency minimums continue to increase, we have to focus on what components are the most efficient during part load conditions, not necessarily full load conditions. And this is actually designed after HRI 340-360. Typically that's for, again, 25% outdoor air and less. On the flip side, you have ISMRE. So very similar, it's integrated seasonal moisture removal efficiency, but that looks at 4 conditions. But one thing you'll notice is now it's truly looking at those exact same conditions entering that unit. So it's not a recirc application. We're really saying how efficient are we at removing moisture from the outside air, because this unit is a 100% outdoor unit, and this is where you need to make sure that we have this. And then one other thing you'll see with this is the weights change as well. A little bit more geared towards full capacity days just because you're designing more of your DOAS equipment for those full capacity days. However, still only 12% is your full load day. And this is test standard HRI 920. And again, this was really laid out to focus truly on those 100% outside air systems. The other thing with ISMRE to point out is If you ever looked at your code breakdown, it never really looked at energy recovery versus non-energy recovery with IEER, because you're always entering at that same condition due to the amount of recirc. With ISMRE, because it's 100% outside air, there are different values and different minimum requirements with energy recovery versus without energy recovery. And the reason being is you can see, for example, on the left, without energy recovery, you have a DX system that is fully responsible to remove all the moisture. When you add energy recovery on, that's a total enthalpy device. So it actually reduces your moisture content as well before it enters the DX system. So even though I'm really humid outside, I'm taking a lot of that humidity out from my energy recovery device. So now my system doesn't have to work as hard, which means I don't have to spend as much energy on the same exact CFM. And that's where your efficiency values are changing a little bit. So where this all comes from, Department of Energy, right now, they only regulate IEER. So as a manufacturer, all of our products, we have to be listed with a minimum IEER that meets those requirements. With DOAS, typically in the past, it's either been misapplied and they've been using IEER for a true DOAS type system, or nobody was really looking at it. And what happened was July of last year, they are now requiring manufacturers to list an ISMRE2 value for all DX DOAS equipment. And then actually today, they were supposed to really require a minimum ISMRE2 value. They don't have their compliance management system built out quite yet, but that is something that they're working on. And again, the big takeaway is manufacturers have to list an ISMRE2 value, and in the future, they'll have to comply with minimums. So you'll get that true differentiation from the Department of Energy that basically says if you're partial recirc or a VAV, you follow these subsets of requirements. And if you're DOAS, now you're going to go to ISMRE2. You'll notice I said ISMRE2 on the last slide. So what changed before they really required this? They wanted to make sure that they fine-tuned some of the test procedures. So reheat is no longer required because applications do or don't require it when you're using this type of system. You can't over dehumidify and take credit for it. So this is basically saying whatever you dehumidify to during your full capacity conditions, you can only take credit for moisture removed to that same leaving dew point, even at your part load conditions. This is just ensuring that your efficiency or you're using high efficient components. And then the last couple are just changing the static pressures, the weights of the conditions, and the actual outdoor conditions themselves to make sure that we are better representing the weather bin data, the applications we're serving, and then we have some more reliable testing that's more representative of actual conditions you'll see in labs as well. So what does this all mean? At a very, very high level, this is why you're seeing so many changes to all of the equipment from an outdoor air standpoint. So DOAS equipment, rooftop equipment, you're seeing the transition from the digital scroll compressors to the inverter scroll compressors. And that is because inverter scroll compressors are 15 to 20% more efficient at your part load conditions. So digital scrolls, great at capacity control, but they're still always using the same amount of energy, even at your part load conditions, versus your inverter scroll compressors, you add that VFD, now you slow down the frequency, which means you get energy savings. Microchannel coils, you get a little bit less pressure drop through the coils. They give you better heat rejection with a smaller coil. You use less refrigerant, so some benefits with the microchannel coils that we've seen. And then AC, more on-off type condenser fans, really getting towards that modulating condenser fan. So EC or VFD driven condenser fans, extremely important not only for efficiency, but if you do ever have applications where you talk about hot gas reheat, that is extremely important to have a modulating condenser fan so you can maintain better reheat capacity in your system. And then the last one, dual circuits to single circuits. A lot of this has to go into account with your coil designs and how much condenser fan energy you have to use based on the highest circuit that's being, or the highest compressor RPMs in that given circuit. So few benefits to single circuit, but condenser fan energy is the main one there. All right, so that was the code and compliance. Doesn't look like we have any questions yet, but again, feel free to add them as you have them. The next section we'll really talk about is going to be air source heat pump. So I know this is obviously very, very big in your market. So general overview real quick, I'm sure you guys are well aware of how it works, but essentially using that same DX system that you'd use for cooling to now reverse the flow of refrigerant and use it for heating. So essentially we're changing our evaporator and condenser coil and just flipping the purpose of those so that in heating mode, we can reject the hot gas from that compressor to that indoor coil and heat up that cold air that's coming in. And then just grab the heat. Even though it's cold outside, we can still grab heat out of that outdoor air. Benefits or advantages, obviously high efficiency. So we're focused on higher efficiency, which means lower operating costs. You can see Seattle in there as an example versus your typical indirect gas furnace. And then also you have a lower carbon footprint. So you're seeing a lot of initiatives, electrification movements across the country to make sure that we have a safe and clean alternative to that conventional heating with that indirect gas furnace. So extremely important that you take advantage of these air source heat pump benefits. But there are some challenges with this as well. So heating performance is directly dependent on the ambient outdoor temperature. So one thing that happens is efficiency will decrease as your outdoor temperature decreases as well. So as an example, I have a true DOAS unit. This one does not have energy recovery. You have 2,500 CFM, 100% outside air. At 47 degrees, so a mild condition when I still need some heating, I have enough capacity to get all the way up to 90.3 degrees leaving air temp. As my ambient temperature drops all the way to 17 degrees, which is normally where we're sitting at, that's a mild condition for Wisconsin. But if we're at 17 degrees, we have a heating capacity of 82 MBH. I can only get up to 47.4 degrees. So the benefit of a furnace, you always knew what your temperature rise was if you had a consistent CFM. Didn't matter what the entering temp was. In this case, you can see I go from a 43 degree temperature rise down to a 30 degree temperature rise. So my capacity and efficiency is decreasing enough where it's directly impacting the overall temperature rise that I can get. So that is really where secondary heat will come into play. And that's that first bullet point you see. Efficiency, if it drops enough, certain climates, those colder climates, are going to require a secondary heat source to make sure you can satisfy that discharge temperature set point requirement. The other things that you have to look at is, are you in an area where your heat pump is going to lock out? So typically an air source heat pump cannot operate below 0 to 10 degrees outdoor temperature, depending on manufacturer. Another thing you'll have to look at is there's certain indoor coil entering air temperature requirements as well. So it's not just ambient. Sometimes it's in conjunction with some minimums entering the indoor coil. But that could be another reason why you would need a secondary heat source. And then lastly is that defrost mode. And so defrost happens when you have the outdoor coil that's grabbing all this heat in, and now we have this frost buildup that you can see on the right-hand side. And this was an actual tested unit that happened at 39 degrees outside, about 80% relative humidity because it was raining. So if I were to guess, that happens quite often in the winter months in the Washington area. So fairly mild temperatures, you get some rain. This could happen, and you need the refrigerant cycle to run in reverse. That basically says, instead of grabbing heat out of the outdoor air, let's discharge it from the compressor, that hot gas, and reject it at this condenser coil now in cooling mode so that we can melt those frost conditions. And in those situations, you need secondary heat or some sort of recirculation so that you can prevent cold air delivering directly to the space. In the testing that we did, we found that whatever was entering that indoor coil, if you were in a defrost cycle, you left that coil about 10 degrees cooler. So in this example, if I was entering at 39 degrees, I would be discharging about 29 degrees off that coil in defrost. That's where you need to size that secondary heat source. Couple other points, the highest frost risk on rainy and snowy days is between 32 and 45 degrees ambient. And this is exactly why we're seeing frost conditions in this 39-degree day. When you're below 32, the surface of the outdoor coil is, liquid precipitation freezes upon contact with the coil surface, right? So it's not going to necessarily freeze the coil. Precipitation is dry snow below 32 degrees. So the snow is less likely to stick on the coil if you're overall below that 32 degrees. And then above 45, you're not necessarily worried about it because the coil surface is not freezing. So that 32 to 45 degrees is that sweet spot where that surface is below freezing, but then you have moisture that's going to freeze on that coil. All right, and then another kind of efficiency topic that you typically see quite often is the energy recovery and the need for economizer. So if we look at the code, typically it says where an economizer is required, the energy recovery system shall include a bypass or controls which permit operation of the economizer. So a couple options that you have is one, you can bypass the energy recovery device. You can modulate or you can stop the energy wheel and you can send it directly through the wheel, but you're not actually using energy to spin the energy wheel. So which sequence is most beneficial? We're going to focus specifically on wheel bypass. And so in this example, we have a classroom wing. It's 6,000 CFM. It's a true DOAS ventilation unit. There's really two options that you would see. One, you would have a 52-inch diameter with bypass, which you can see on the left. You have to shrink it down to fit this bypass damper in, if there was one. And then the second one is you could size that wheel for as large as possible, but in those situations, you couldn't fit a bypass damper. So now you have to make sure that you have some other control strategy in place. So a couple things to note. When you look at just the energy wheel, the larger energy wheel has a lower pressure drop in normal operation, right? So the whole idea of using bypass dampers during economizer is to avoid the pressure drop of sending that free cooling air through the energy recovery device. So on the contrary, you actually raise it during normal operation. So you look at the fan energy, if you're 5 days a week, 12 hours per day, or 24/7 type operation, this is just fan energy. The one thing to keep in mind, and one that is incredibly important in the Washington market due to the Washington State Code, is you have certain energy effectiveness requirements minimums as well. And when you shrink your wheel down to this 52-inch, now you're actually going to lower your overall effectiveness at the same time. So you're lowering your effectiveness, which means that you're going to require more heating capacity downstream. And then you also have more fan energy during normal operation as well. So that always then comes to the question of, well, how often do I have to have this bypass damper open to match the 58-inch wheel fan energy? And the answer to our study was about 40% of the time. That assumed a 50% pressure drop requirement. That is an assumption, not always true, but that is how we match the fan energy. Again, the other thing to keep in mind is how often does it have to be open to match that heating and additional cooling capacity required as well. So a couple things that you want to consider. Now, where does it make sense? In those VAV type applications. So in this example, we're not 100% outside air anymore. We have partial recirc. In this case, we have 12,000 CFM of supply, but we only are designed for 3,000 CFM at most during normal operation. So that's typically how that wheel is sized. In bypass or in economizer, now we actually have 12,000 CFM potentially coming through that wheel. Well, that wheel might not be sized to handle that full amount. That is when you need a bypass damper so you can prevent wheel damage. In those DOAS applications, you already have a wheel sized for that 100% outside air. So that's where it makes sense to just size it as large as possible to get the most effectiveness and the least amount of pressure drop during normal operation. A lot of content covered, more industry specific on there. So if you have any questions on the first part, let me know. Otherwise, we'll dive right into the refrigerant transition as well. All right. So this is a hot topic around the country right now. I'm not sure how many of you are aware of it. We'll cover as much as possible today, and obviously as questions arise, reach out to Dorsey and we can continue to get you some answers as well. So why are we changing refrigerants? When you look at non-vehicular HVAC refrigeration, it constitutes 66% of all HFC emissions. So it's quite substantial in this market. And then when you look at the HFC refrigerants specifically, those are ones that are often high global warming potential chemicals, or they include high global warming potential chemicals. So that was something that they found due to the emissions, the global warming potential. They wanted to make this change. The caveat to this, right, is change is constant. So I would continue to expect future changes, future clarifications. And the reason being is standards, codes, regulations, they all require consensus from everybody involved. Problem with that is consensus does take time to just understand what's happening. It takes time to build consensus around the country and within states. And not all items currently have been resolved, have been clarified. So that's really where we're at today. We're providing as much information, but certainly things are going to continue to change as we progress with this refrigerant transition. But the updates, really to get into some more detail, the EPA passed what they're calling the technology transition rule. And this is limiting your refrigerant global warming potential to 700 at most for all residential and light commercial air conditioning and heat pump applications. You look at the table on, or the graphic on the right, our 410A that we use today has over a 2000 GWP value. So well exceeding the threshold of that 700 set by that technology transition rule. And when you look at the common replacement, R454B is what we've seen the most of so far. R32 is certainly going to be a used refrigerant as well. Both of those are under that 700 GWP value. You can see 454B goes a little bit lower. Nonetheless, they both are under that threshold. The other thing to point out in that graphic is the safety classification. So we are moving into A2L safety classification territory, which means a mildly flammable refrigerant. So there are additional safety requirements that come with it, which we will discuss throughout. So manufacturing, what does this mean from a date? For us specifically, new 410A equipment cannot be manufactured after December 31st of this year. So we're about 7 months away or so that we have to start transitioning this over. And with that said, if you're still purchasing equipment today or laying out 410A equipment, the replacement components can be manufactured indefinitely. So similar to R22, still going to be able to replace those components in the field. And then there is some sell-through and installation requirements as well. So for new products, you actually have a 3-year sell-through window. So think about your kind of commodity rooftop type units. If they're manufactured and stocked before December 31st, they can sell those for a period of 3 years. So it's just all based off of the manufacturing date. And then any like new systems, so your split system designs that aren't considered finished until they're actually piped in the field, that is a 1-year sell-through, as long as they're manufactured before that December 31st date. So hopefully that clears up a little bit on that introduction. There's some deadlines here in this table. So one thing is, obviously when you look at the U.S. Climate Alliance states, there's some adoptions that already started to take place, specifically in those small residential type equipment that you see in the first product category. So the EPA deadline was January 1st, 2025. But California, Washington, for example, January 1st, 2023, they started to leverage the low GWP type refrigerants. Chillers, January 1st, 2025 for EPA. This January 1st, 2024 for the Climate Alliance states. We are in this other residential and light commercial AC. So January 1st, 2025, that's really that December 31st deadline that we talked about. And then a year later will be the VRF products, more of the indoor type equipment that you'll see. So those are some deadlines that we're working with right now. The question is, okay, I understand we have to do this, but how is it going to impact your day and your responsibilities? Well, first thing, there's new code requirements. So all the mechanical codes, the refrigeration codes, there's going to be updates and different requirements in certain situations. On top of that, there's additional installation considerations that have to be accounted for. So there's product safety standards. For example, we are transitioning to UL 60335, and that carries additional considerations from an installation standpoint. Additional design and coordination requirements, whether it's controls coordination, which we'll talk about. You might have to specify some certain design requirements for spaces that actually have refrigerant piping and systems within them. And then you might actually have to design mechanical ventilation systems where required as well. And then lastly, the most significant one is obviously there's legal ramifications from the EPA if you install systems after regulated dates. So that's a violation of the technology transition rule. Manufacturers are adhering to it, and then obviously the field would have to from that sell-through or installation date standpoint as well. And then one disclaimer before we go through the next few slides here is, we're all starting this journey. It feels like we probably should have started it a little bit longer ago if it's a December 31st cutoff, but every single day there is new guidance, new codes, new standards that are being updated. So this is the best information that we can share at this point, trying our best to help bring you up to speed with where we are on the journey, and then obviously some certain requirements that you might have to implement in your design strategies as well. So authority review is the first main point, and building codes generally are the ultimate authority, right? So when specifically noted, building codes do give the authority to any product safety, any industry standards that exist, and they normally are part of those building codes. But conflicting information, so differences between the two, has a pecking order, and that starts with building codes. So if there is a certain nuance within a building code in your area, that is going to win out, even if it references like a safety standard from our equipment. So always important to look at your local building codes that you're following. And then lastly, don't forget about the alternative materials, design, and methods of constructions for compliance. So in most codes, there is an alternate methods option that gives the inspector the ability to approve that. So something important when you're looking at that as well. Three main areas of authority. Obviously, I talked about the local codes. So this is where you're going to see your mechanical codes, some local fire codes as well. And then that is really followed by the product safety. So product safety must follow the installation requirements. As I mentioned, this safety standard is going from the UL 1995 that exists today to the UL 60335-2-40. That is something that most mechanical codes will reference, but again, there are some codes that locally they can change some tables, add some additional requirements, and then you have some standards that are typically referenced in both the local codes and the product safety as well. Things like ASHRAE 15 or maybe some residential standards as well. Okay, so A2L refrigerants. That is that safety classification, and the main concern here is they are mildly flammable. So the big concern is what kind of leaks might I see and how should I plan for them? There's three main types of leaks that we're looking at when it comes to equipment classification. First one is outdoor mounted equipment, and that is where you're going to see component failures within the equipment that will leak refrigerant into the occupied space through the duct connections. Next one is what happens when equipment's mounted in the space itself. Well, now you have additional piping, you have equipment location, and then you have still that ducted service area that are all leak paths that need to be evaluated. And then lastly, that mechanical room, it's the same as your space pond, but there's additional considerations due to the confined space that unit would be installed in. So there's some other hazards that could come along with a mildly flammable refrigerant in those small spaces with such a big charge. When you look at DX air conditioning and heat pump equipment, they're classified as direct high probability systems. And what that means is they're dictated as an equipment that can, or where an individual component failure directly leaks refrigerant into that occupied space. And it's a high probability that if there's a leak, it will leak into that space. So the question is, okay, we're planning for those leaks. How should we address the leak potential? And building codes, safety standards, they're all doing it a little bit differently while also trying to reference each other. So building codes and ASHRAE 15 are specifically looking at a maximum charge allowed based on your expected dispersal volume. So overall, your area that we can disperse this leaked refrigerant into, there's a maximum charge associated with that. The UMC is basically verbatim with ASHRAE 15. The IMC is a little bit more conservative and independent of ASHRAE 15. So some other differences there. And then you get into the product safety standards piece. There is minimum room or conditioned space area requirements. And typically that's going to have to be provided in all of the manufacturer IOMs. So we are including that in our IOMs. This does follow ASHRAE 15 closely for non-institutional occupancies based on where you install it and then the leak height as well. And we'll cover some of that as well. And then the biggest thing is check your occupancy classification, because institutional occupancies in general, they allow 50% of the refrigerant charge that other occupancies may allow as part of these tables. So a little bit more strict if you're designing around those institutional occupancy designations. So mitigation strategies, great. Understand that there's some things that might happen. How do I actually handle the mitigation requirements? Air circulation is that first one. So air circulation is used to distribute that leaked refrigerant evenly throughout a room. And that is for room mounted equipment or to multiple spaces for ducted systems. So again, air circulation, let's just move as much air into these areas as we can to dilute the refrigerant. Ventilation is used to remove leaked refrigerant from a space, either to adjoining spaces or outdoors when charged exceeded initial space volume requirements. So if my unit's refrigerant charge is over what it could be for a certain space, and I don't have ducted systems that I can diffuse or distribute this to evenly, you might have to design ventilation in the space itself to take care of any leaks. And then the last one is what we call releasable charge controls. And this can be used to minimize the actual charge that's released into the space, and you could actually avoid the need for air circulation. So it's only available on smaller equipment, VRF, cassettes, small indoor units. Basically what that's saying, if there's a leak at the condensing unit or something upstream of this equipment, we have a shutoff valve or something that eliminates that refrigerant from getting into the space itself. When we do that, we might not have to turn that air circulation on. So a few mitigation strategies that will make more sense as we get into either today or future training that we might host. So talked a little bit about volume and space requirements. So what are some considerations to think about? First is plenum spaces. Plenum spaces may be considered as part of the dispersal volume. So it's not just the space itself, but you can also look at the plenum requirements. Ducts, so duct volume may be considered part of the dispersal volume as well. Rooms where control dampers completely close cannot be counted. Partitions, because this A2L or R32 and 454B refrigerants are more dense, they tend to settle at the bottom of the space. So depending on how high the partition is, it may limit the available room size that you can use as part of the distribution space area. And then lastly, ventilation between rooms. So mechanical and natural ventilation options are available to account those different adjoining spaces as the overall square feet of area that you have to distribute refrigerant to. And so where that comes into play is there are certain installation requirements. This is just one example. Typically, there's a different row in the codes like this for about every pound of refrigerant. And this example, we have a 101 pound circuit. So that's the big thing to keep in mind is it's not based off of total system charge. It's based off of the single largest circuit if you have this refrigerant. And so in this case, if we had a 101 pound single circuit design, you have to basically the minimum that you can serve as far as your space floor area is 1,464 square feet. Okay, so that's the first thing. If the equipment is in the space itself, then basically you have your piping in the occupied space. That room must meet the area in green as well. So it's dependent on release height. So where is the lowest amount that refrigerant could be released from the floor? There's additional room area requirements that you have to have if you want to install that into that space. So in this example, if you had a connection or something at 2 feet or less, it would actually go up to 5,372 minimum square feet that you would require. And then when you look at just overall minimum airflow, the unit must maintain 2,643 CFM in this example of that air circulation strategy when a leak is detected to distribute into that space. So a lot of that is going to come from a manufacturer. Like we are going to have requirements that if we experience a leak, we would have to maintain a minimum airflow based on our refrigerant charge. So hopefully that makes sense. More to come when we put the tables in our IOMs and in our submittals as well. All right, so how do we integrate these products, specifically outdoor air type equipment? You know, the product itself likely will have a refrigerant detection system to perform whatever required sequences we have to make sure we are meeting the safety standard that UL 60335. However, there are things downstream that we have to integrate to and make sure that everything downstream is handled effectively with leaking refrigerant as well. So first example, must shut down electric heaters in the ductwork if we experience a leak at the unit with ducted systems. All zoning dampers have to be opened up, again, if you want to count those spaces and avoid overpressurization of ductwork. That's important. You have to de-energize space and duct ignition sources, which we'll talk about next slide. And then if you need any additional mechanical ventilation, if the space is too small for that refrigerant charge, that must be triggered at this point as well. So what do we mean by ignition sources? First one is any open flames. Sometimes these are not allowed in the space to begin with, so some codes will lock that out. But assuming we have a leak in the unit on the roof and we go into that sequence, open flames must be placed out. And then electrical sources of ignition is based off of an apparent power volume. So if it's greater than that 1 kilovolt ampere, basically you have to shut down that source of ignition. And then anytime that you have a high temperature device, that is also classified as something that you must shut down. That's basically 1,290 degrees or hotter, unless you maintain that 200 minimum feet per minute requirement. So it looks like we have a question. How will the units communicate the refrigerant leak? Is there a back vent alarm? So I'll answer that part first. So 2 things. 1, there will be an alarm if you do have a building management system. Number 2 is we will have contact closures that we will communicate to. So essentially when we are experiencing a leak, we actually override our controller and we will send a signal either to the BMS that way, or you can have a contact closure that you can tie off of and use to then shut down things downstream. So that's that first piece. And then on a variable volume system, will the unit maintain the minimum CFM, or will this need to be part of a control sequence? So for all of our products, we will have a minimum, basically based on the housing size and the tonnage, we will have a minimum fan speed that we will have that this is essentially controlling to. So that will be communicated out. We're still finalizing some of our designs. If we go back 1 slide, oh, sorry, no, right here. There's certain feet per minute that we have to maintain in all these products. So we're just doing some testing to make sure that we can maintain those minimum feet per minute. And then obviously we'll try to communicate what that minimum is that we'll be turning on to. So a good example of there's enough information to tell people that this is going to have to happen, but not enough information where manufacturers and controls contractors and everybody is going to be on the same page right off the bat. So as we get more information, we are trying to create more of like a resource center that we can continue to put some information on that you guys can come out to, or Dorsey can present to you as well. And that segues into just some resources available if you want to learn more about this. ASHRAE 15 and obviously that refrigeration code, there's free read-only versions online. So, you look at the addendas, the interpretations, things like that, but that is a resource that has some of this information in it. UL 60335, obviously that's a safety standard. You can reach out to manufacturers for more information on product requirements if you have some additional questions. And then obviously your mechanical codes, extremely important to look at all the resources and those specific codes that are associated with the mechanical codes. Last one is there's a safe refrigerant transition website and code adoption map for AHRI. So I have an example on this slide right here. So for Washington, you can see, most of the codes have been updated. You can see what standards you're currently referencing. But if you're designing in a different state, you might want to check out what codes they have. And a lot of times what this is showing is Washington's above the game, but like Wisconsin, for example, where I'm from, we don't update codes very well. So you'll see this legislation. This legislation basically means that you can install something. So nothing is preventing that state from installing A2L refrigerants. But if they don't have their codes updated, they don't give direction on how to install it or service it safely. So it's basically, go ahead, we're not going to stop you because we know manufacturers have to, but we're also not providing any direction on how to do it. So that's where it gets a little bit tricky, wanting to really make sure that we push all the states to start adopting all of these refrigerant codes. All right, so that was a lot of information on refrigerants, and we have about 10 minutes left. Should be perfect enough to cover the Green Heck DOAS equipment, but are there any other questions on the refrigerant transition specifically? All right, so all done with the code stuff. We'll talk a little bit about the DOAS equipment and what we offer. So obviously talked about everything strategically for a reason. A lot of it applies to this equipment, specifically the applications served, the high percentages of outside air. But we actually have 5 cabinet sizes right now. As Chris mentioned earlier, it's our RV, RVE, and RVC product line. Goes anywhere from 500 up to 18,000 CFM, anywhere from 3 to 70 tons of cooling. And then you can get energy recovery. So on the bottom right there, you see all the energy recovery options. The RVE is with our enthalpy wheel, and that's going to be polymer or aluminum wheels. RVC is going to be polymer or fiber enthalpy core. So everything is a total enthalpy device, wheels and cores. As far as heating options go, we do have indirect gas. We can do SCR controlled electric heat, hot water coils, and then the air source heat pump currently goes from 5 to 30 tons. So not the full product breadth, but as we get to this electrification movement and we get the refrigerant transitioned over, you will start to see some expanded tonnage ranges there as well. Cooling options besides the air source heat pump, package DX, and chill water coil. As far as construction goes, this is really where you start to see some differentiation between your traditional rooftop equipment and then a true high percentage outside air unit. Coating, want to make sure that this unit lasts as long as possible. Our coating is a standard kind of pre-painted panel. We call it a permatector. It's this concrete gray color, but it carries a standard 2,500 hour salt spray rating. And then insulation is really the biggest piece here. So we're double wall construction, and then we have 2-inch R13 injected foam insulation. So it's not foam board, it's actually injected foam that improves the rigidity and the sound deadening of that material as well as increasing the thermal resistance with that R13 value. So we standardize that on all the walls, the ceiling, and the base. So beyond the thermal resistance, you get some really nice protection from sound related to the components inside. So simplifying installation. So one thing we like to make sure that we have high quality components, they work well, but we also want this to be easy to install. So a couple ways that we do that. One is horizontal discharge and return configuration options. This removes the need for the plenum curb. So whether you have side supply in return, you might have some end return options. This gives you the benefit to pad mount it or keep a low profile design and eliminate the need for a plenum curb with a potential service platform, but still get the benefits of the horizontal connections. The other thing that we just started to introduce, it shouldn't say coming soon because it is here now, is the QR codes. So when you get out on site, these units will have a QR code. That is a direct link to all the manuals, all the frequently asked questions that our service team gets, startup documents and startup videos, so that whoever's starting up this equipment, they have direct access to all of the information that we put out there. There will also be a direct line to text service from GreenHeck as well. So if they cover all the documents, they want to try to do it themselves, great. If not, we have a group of dedicated people that are willing to help you out as well. Sound. So I mentioned 50% of our equipment about goes to education. So obviously when we have schools and neighboring residences next to playgrounds, whatever it may be, sound's usually an issue. And so we standardize on some components like the low sound condenser fan. So that is a standard condenser fan. You don't need an acoustical package of any sorts. And we include a lead condenser fan, ECM, as standard as well. So that really reduces, especially at part low condition, your overall sound. And then internal, anything above 7 tons where we get to some larger equipment, we have the compressors always mounted on an elevated shelf in that insulated cabinet. And again, that includes that standard base insulation. So even if the compressors are mounted on the base, it's an inverter scroll compressor and it's insulated on that base, so you don't have any noise radiating through that base, through the ceiling into that space. Controls. So we have a standalone controls option with building management system integration. And a couple things here. One is our controller is just a skeleton that we get from Corel. So based on all the different applications that we talked about, this controller can be configured based on how it's ordered for that application. It's factory programmed. And then if you have a building management system, the submittal comes with a dynamic points list. So based on selections, what points would you have the ability to read? What points would you have the ability to communicate to? And then we also have an integration guide that's on the bottom right that really takes it and goes more in depth of how do you use that point? What are the minimum and the maximums? What is it default to, so that you can easily configure that in the field as well. And then lastly, we have a standard web user interface. So anytime that you get a microprocessor, basically you will have the ability to take an Ethernet cable, run it down to the building network, and connect to this web user interface. When you're connected to this web user interface, you just punch in an IP address when you're on that building network, and you can see how this unit operates. You can see up in the upper left there, you can see I have a settings tab, shows me kind of the main settings of that controller. Alarms tab gives me the ability to look at all of my alarms historically. I can see some trend data, and then the unit display here actually gives me the ability to act as if I had a remote mounted display for that controller. So it's a direct mimic of that microprocessor screen. All controllers come with a built-in LCD display, but some main benefits are you get that remote mounted display. And then control options, won't cover this too in depth here, but you can see obviously supply fan, partial recirc dampers, and exhaust fan. A lot of different options. If something changes in the field to benefit with our controller, it's very easy to switch from one of these to another without a big program update. You just get into this menu for dampers, change it from space pressure to constant position, and that's how it's going to be operating. So very easy to make on-the-fly adjustments as well. And then reliable manufacturing quality. So won't spend too much time on the next couple of slides because I know I'm running out of time, but basically, we have a full fabrication automation process in each one of our plants. Helps us ensure consistent quality. This is just a screenshot of as it was getting set up. And then obviously we have weigh-in charge machines, a thorough end-of-line testing and audit. So about a 90-minute test for every single unit that comes out of our factory with a detailed factory test certificate as well. So we really care about all of the manufacturing quality as well. And then reliable shipments, we have plants in Tulsa and Kings Mountain. We're continuing to expand all of these. We have about 430,000 square feet of production space dedicated to just DOAS equipment. So pretty incredible operation there, which then takes us into our current lead times. COVID was bad. We were out to that 30 to 40 weeks like most people were. But you can see based on the tonnage breakdown, we're down to that 8 to 14 week lead time. And I would say our target is actually 6 to 8 weeks. So we're not even close to where we want to be. The manufacturing plants that we have in place have a lot of benefits coming there as well. And then just to respect time, I'm going to go to the last option here, or last slide, just to kind of show you what's coming next. I can get Dorsey guys a slide deck so you have them, but compliance initiatives we talked about, product enhancements we didn't necessarily talk about. So our 3 to 7 ton unit, we are actually adding energy recovery to that. We're aiming for this August, so an energy recovery wheel there. Air source heat pump expansion. So we're going to also go to that 3 to 7 ton with the air source heat pump first. And then we're going to look for larger than 30 ton air source heat pumps. And then we're actually currently working on a larger capacity up to a 100 ton unit. And then working on some quick build programs as well. So subset of selection accessories that you could use to then get things really quick if you do need them. And that is, I say all I had very lightly because I know it's a ton of content, but the refrigerant transition is quite robust. So any questions that you guys have? Oh, I think you're muted, Chris.
I think I'd have that figured out by now too. While we're waiting for any questions in the chat, Jake, thank you as always. And I always like to tell individuals, like, there's no way you can remember everything Jake talked about. We just want you to know that Greeneck probably has a solution. They're experts at what they do, and to remember to give one of your Dorsey engineering reps a call, or if you're a contractor, your account manager. We're happy to do one of these presentations ourselves. You know, if you want to focus on product a little more, talk about the air source heat pump. That seems to be one of the big things, Jake, we do, is the air source heat pump with supplemental electric heat. That is a really hot product in terms of, you know, corridor ventilation. We're constantly seeing it both with and without energy recovery. So yeah, again, if you want to have one of these presentations for your own individual firms, please let us know. Still not seeing any questions in the chat. We look forward to seeing everyone next week. I believe we're doing Venturi valves next week. So if you haven't signed up for that, please do. We'll make sure you get the link. I don't see any questions. So everyone have a great day. And Jake, as always, thank you. Yeah. And we look forward to seeing everyone next week.
Yep. Thanks, guys. Have a good one.
Thanks, Jake. Thanks, everyone.